Okay, so similar to the previous problem, let's launch an object from a height L. And let's say we launch it at some angle, at some speed v naught at an angle alpha above the horizontal. And so the object will clearly move. Let's sort of try to draw the path. It will go like that, and it will come down and eventually hit the bottom. But let's ask the question, what is the speed of the object when it's still at a height which is L over 2? Say there. What is the speed of the object at that height? So, right, the speed, of course, is Vx squared plus Vy squared square root. And the Vx component is unchanged because there's no acceleration in the horizontal direction. So it's just the horizontal component of this. So it's V naught cosine of alpha. So we have that. And we'll put it into there. We need the Vy. And the initial, the V naught y, is V naught sine of alpha. And it's positive because the vertical component is upwards, and our convention is that upwards is positive. But over time, that value changes, and so we need to figure out the time t when the object is at this height. So that forces us to the second, or the first kinematic equation. Right, so when the object is at a height L over 2, right, y equals y naught, and y naught is L, plus V naught yt, which is V naught y is this. So we have V naught sine alpha t minus 1/2 gt squared. And so we see that we have a quadratic equation, but let's write this so that we can combine the distances. We will subtract L over 2 here, and so we'll get L over 2 here plus V naught sine alpha t minus 1/2 gt squared. And so t becomes what? T is minus b, so it's minus V naught sine alpha plus or minus the square root of b squared, which is V naught squared sine squared of alpha. B squared minus 4ac, so it's minus 4 times a is the usual minus g over 2, minus 4a times c, and c is L over 2, so this term becomes positive. And we have to divide all of this by 2a, and so we get minus g as usual on the bottom. And so we have a minus and a minus, that's a positive, so we have a V naught sine of alpha over g term. And then we have to choose between two possible solutions, V naught squared sine squared alpha plus the 4 here cancels with the 4 here, so we have plus g times L, and this is divided by g. All right, again, the minus sign here gets incorporated into the top part because we will flip the plus to a minus and the minus to a plus, so we still have a choice there. So we still have to pick one. And notice that if we get rid of the GL term and we take the square root, then this just becomes this. And so if we subtract, that would give us 0. And so given that we have this extra term here, if we choose the negative, then we get a negative time, and what we want is a positive time. So that seems to suggest that the only reasonable solution is the one with a positive. So we have V naught sine of alpha over g plus the square root of V naught squared sine squared alpha plus GL square root over g, and that's our time. And we'll plug this into the Vy equation where the t is and get Vy. So Vy is now equal to V naught sine of alpha minus g times this. That simply gets rid of the g in the bottom. So we have a minus V naught sine alpha. But that turns this one into a negative. So we have minus the square root of V naught squared sine squared alpha plus GL. And so this cancels with this. And so we end up with a minus square root of V naught squared sine squared alpha plus GL. And we have our Vy. And now we can construct our speed at that height, which is the square root of Vx squared, which is V naught cosine alpha squared. V naught squared plus our Vy is here, so we'll just get plus V naught squared sine squared alpha plus GL. And we have to take the square root of that. Of course, these two add up to V naught squared, and we have plus GL. And of course, we'll take the positive root because we want the speed. So that's our speed at that height.